Welcome to The Explainer. Today, we're setting out to demystify the absolute bedrock of our logical universe, numbers. Think of the number system kind of like a massive video game map that humanity has been slowly unlocking over thousands of years. Today, we're going to explore that map step by step, starting from the most basic tools of survival and zooming all the way out to the very edges of mathematical imagination. It's going to be a fun ride. To make this whole abstract universe a bit easier to digest, here's our roadmap for today. We'll kick things off with what are numbers, move into building the foundation, then filling the gaps. After that, we'll dive into the ultimate collections, map out the family tree, and finally wrap up with some really cool special number traits. All right, part one. What are numbers? Before we start categorizing them, we need to understand what they actually are. At its core, a number is strictly defined as a mathematical object used to count, measure, and label. I know, it sounds almost too simple, right? But this is literally our ultimate translation tool. It takes all the physical chaos of the real world and turns it into organized, logical information that our human brains can actually process and communicate. Let's ground this abstract idea right into our everyday reality. We use numbers to measure portions of a whole, like slicing up fractions of a pie. We use them to label sub-zero temperatures on a thermometer to track global climate patterns. We use them to count the endless chaotic fluctuations of the stock market. Truly, every single aspect of modern human life relies heavily on this one mathematical object. Moving right along to section 2, building the foundation. Let's look at the earliest numbers humanity ever used. Let's crack open our first mathematical matryoshka doll and look at the absolute foundational layer. We begin with natural numbers. These are simply the numbers we use for counting and ordering. Imagine you're an ancient shepherd keeping track of your flock. These are literally the only tools you need. 1 sheep, 2 sheep, 3 sheep. It's simple, it's highly intuitive, and well, perfectly natural. If you picture a natural number line, it starts at exactly 1 and moves endlessly to the right in solid whole steps. 1, 2, 3, 4, 5, and so on. It perfectly solves that basic human problem of counting tangible things. But then, humanity ran right into a philosophical and practical wall. Think about it. What happens when you have absolutely nothing? To represent an empty pasture or a completely empty bowl, we needed a massive conceptual breakthrough. We had to invent zero. And with zero, we created whole numbers, which are just the counting numbers we already knew, plus zero. By doing this, our mathematical map literally unlocked a brand new space to the left. We still have all our natural numbers, but the line now officially starts at 0. We finally captured nothingness as a concrete mathematical concept. Of course, human society just kept getting more complex. What happens if you owe someone 3 sheep? Or what happens when the temperature drops below freezing? You can't just say you have nothing. You have a deficit. You literally have less than nothing. So, to represent this, we expanded the system again and created integer numbers. These encompass your positive numbers, 0, and crucially, your negative numbers. Now, our number line brilliantly mirrors itself. From our 0 point in the middle, we step to the right for positive integers, and we step to the left into negative integers, perfectly opposite to one another. Debt, freezing temperatures, financial deficits, they can all be perfectly measured now. Okay, on to section 3, filling the gaps. What lives in the empty spaces between these solid numbers? If you look closely at an integer line, it's just whole solid steps. But reality isn't always whole steps, is it? The spaces between integers are populated by 2 very different characters. On one side, we've got rational numbers. These guys behave neatly and can be expressed exactly as a ratio or a fraction. On the other side, we have the rule breakers, irrational numbers. These absolutely cannot be written as a simple fraction. So, rational numbers swoop in to fill those in-between spaces. A rational number is basically any number you can express as a ratio of 2 integers. Think of it as p over q, as long as q is in 0. So, -3 halves or 5 halves. We're slicing up the spaces between our whole numbers into perfectly predictable, measurable fractions. But then you have the chaotic beauty of irrational numbers. These are decimals that go on forever and ever without repeating any kind of pattern. You just can't write them as a neat fraction. Famous examples you probably recognize are pi, which we use to measure circles, Euler's number e, which is absolutely essential for calculating growth, or the square root of 2. They live right there on the number line, but they are infinitely complex. All right, section 4, the ultimate collections. It's time to take a massive leap into the mathematical imagination.
We've covered a lot of ground so far. Now, we're going to take everything we've learned and throw it into one master container. Meet the real numbers. This ultimate collection includes literally everything we've talked about, rational and irrational. Every single point on a continuous, infinite line, whether it's -3, 0, 1/2, or pi, it is a real number.
But, mathematics never really stops. What happens when you encounter an impossible problem? Like, say, trying to find the square root of a negative number. You have to enter the realm of complex numbers, the final boss of math. A complex number takes the form a plus ib. It blends a, which is a real number, with ib, where I is the imaginary unit. And I is totally unique. It's defined as a number where I squared equals -1. This wild conceptual leap unlocks entirely new dimensions in advanced physics and engineering. Section 5, the family tree. Let's take a breath and zoom out to see the big picture. We've gone all the way from counting literal sheep to imaginary mathematical units. So let's look at the complete map of everything we've uncovered. Top down, we have all numbers. They split into complex and real. Those real numbers break down into the chaotic irrationals and the neat rationals. Rationals break down into fractions and integers. Integers split into negatives and whole numbers. And finally, whole numbers hold the invention of 0 right alongside our foundational natural counting numbers. It's a pretty beautiful family tree when you look at it all together. And finally, section 6, special number traits. Let's look at some fun personalities hidden in the numbers. For our final act in this explainer, we're going to zoom all the way back down to our oldest friends, the natural numbers, because they have some really special traits. Natural numbers can be categorized by strict divisibility rules. Evens are perfectly divisible by 2, odds are not. Then we have prime numbers, which are basically the building blocks of math, only divisible by 1 and themselves, think 7 or 11. And coprimes? Those are a pair of numbers that share absolutely no common factor other than the number 1.
We also have composite numbers, like 4, 6, 8, and 10. These are formed by multiplying two smaller natural numbers together. And then there are perfect numbers. These are just fascinating. A perfect number is one where if you find all its factors and add them together, they equal the number itself. Take 6, for example. The factors are 1, 2, and 3. Add 1 plus 2 plus 3, and what do you get? Exactly 6. 28s, 496, and 8,128 do the exact same magical thing. So we've explored the map of numbers from the absolute simplest counting tools to complex imaginary dimensions. But here's the biggest takeaway from this explainer. The map is still being drawn. Mathematics is a living, breathing language. So I want to leave you with this final thought-provoking question. If numbers are truly infinite, what other incredible systems are just waiting out there in the dark for us to discover? Thank you so much for exploring with me today. And hey, keep that curiosity alive.